Okay, at this point we realize that we always end up measuring the speed of light as the speed of light. So even if we're moving again at our usual 260, the clocks become offset, the clocks are ticking slowly, the length is shrunk. So if we send a burst of light, I mean, a burst of light could have occurred over here somewhere, and let's say they end up seeing it at this end, and then later on they see the burst of light at the other end, and they'll measure it as being the speed of light. So to an external observer, the light is moving across at the speed of light, and as far as they're concerned, it's still moving at the speed of light, even though relative to their spaceship, it's only moving at 40,000 kilometers per second. But what's interesting is, in the world of physics, they also found out that if a moving body emits light, such as our spaceship here, so let's say we have our spaceship, it's got a light on the front and two tail lights, and it's going at our 260, the velocity of 260, the light emitted from the front will be emitted at 40,000 kilometers per second. So you have the speed of the spaceship and the light bulb here to begin with moving at 260. Then you add the emitting speed of 40,000 kilometers per second. So the end result is the speed of light for the light moving across space. So again, in this direction, that means the light is emitted at 40,000 kilometers per second. The light going in the opposite direction from the tail lights is emitted at 560,000 kilometers per second. So you take the 560 minus the velocity of the spaceship, because it's going in the opposite direction than the light is going. Once again, you end up with the speed of light moving across space at 300,000 kilometers per second. So you think, this is kind of bizarre. How do these little photons, those are particles of light, know to only be emitted at 40,000 kilometers in this direction and at 560,000 kilometers per second in the other direction? How can they be so smart? And if you ask today's physicists, they don't quite have an answer to that. They just basically say that the speed of light is always the speed of light. It's always observed to be the speed of light, and observed means measured. You use your measurement instruments. And it's always emitted, or it's always, even if the light is emitted from a moving body, the light will be moving across space at 300,000 kilometers per second. So the speed of light is consistent. So you wonder, how exactly does that happen? Well, you recall that if you start moving across space, rotation occurs, right? And anything that emits a photon, such as an electron, which is orbiting around a nucleus at the center, this is spinning. So you can call it a spatial spin, right? So basically you can look at it like this. And there's your electron, and there's the axis, and it's spinning across space. But as you recall, as soon as you start moving across space, rotation occurs. So if you're going in our famous 260 direction here, you end up with a spin which looks like this. So this here is time, this is space, and the electron is spinning across time. The axis is now extending across time as well. And so it's going down across time, then up across time, and so forth. And so if the electron throws off a photon when it's going in this direction, it's slowing down in time. Because, yes, the electron to begin with is moving through time, because it's moving both across both space and across time when it's going in this direction. But now it's going downward across time, and so it's going into a very slow time frame. And so if the photon is thrown in this forward direction, because notice when it's coming down, it's going the forward direction across space, it will therefore emit the photon in a slow time frame. Or when the electron comes around here, let's say emits the photon in the backward direction, now it's rapidly going across time. So not only was it going across time to begin with, due to this direction of travel, it's now rapidly going across time. So it's in a very fast time frame, and thus the light in this direction, thrown off, released from the electron, is thrown off in at 560,000 kilometers per second. So it's all due to this rotation occurring. Now, another way you can look at this as well is with a particle known as a meson. And when a meson decays, it splits into two photons. Those are particles of light. So you have photon 2 and photon 1. But of course, they're moving at the speed of light, because they're particles of light, in opposite directions. So in this case, you just imagine that the meson was just moving across the dimension of time, and now when it decays, you have two photons moving across the dimension of space in opposite directions. So you can think of this, when it decays into two photons, you can think of two photons that are spinning around like this, attracted to a central core, a nucleus, right? And so they're kind of bonded together, spinning around. However, when rotation occurs, if this meson was moving across space, so you're not just moving across time now, but you're moving across space as well, then you end up with this type of an effect as well. It's rotated. That spatial spin is now extending across time. So here you'd have photon 2, and over here you have photon number 1, and it's spinning around. And so in this case, again, the photon that's thrown in the forward direction is going down, reducing the overall motion across time dramatically. Thus, it throws it off in this direction, emits it in this direction at 40,000 kilometers per second. The other one that goes in the opposite direction is going up across time. So you already have the previous motion across time in combination with this sweeping or spinning as it's moving across time. This one is emitted at 560,000 kilometers per second. That's all assuming that our meson was moving, or meson was moving at 260,000 kilometers per second. So because of this, you always end up having the light that's emitted going across space at 300,000 kilometers per second. 260 plus 40 equals 300,000 kilometers. 560 minus the 300,000 kilometers. Sorry, 560 minus the 260 again equals 300,000 kilometers per second. So that makes it easy to understand why the speed of light is always ending up being the speed of light. And again, so that is, the speed of light is just an outcome due to this constant motion and rotation and so forth. The constant speed of light is an outcome of that. And so when you're dealing with these equations, the best thing to look at, the letter C, as far as representation goes, is this constant motion, which is the same speed as the speed of light is across space. But in the world of physics, Einstein started by analyzing light and discovering that it was consistent in no matter what. And when you measure it, you always measure the speed of light. When it's emitted, the end result is it's moving across space at the speed of light. And never did really backtrack to the point of showing the foundation which I revealed, which shows you how to create all these equations in the first place. But in the world of physics, like Einstein's world there, a lot of these equations existed before he came up with his idea of special relativity. That's why this one's called the Lorentz-Fitzgerald contraction, not the Einstein contraction. The Lorentz transformation equations, not the Einstein transformation equations. But in my case, by examining the foundation, I come up with all of them from one analysis of motion and so forth. But it also helps you understand exactly what's happening to the measurement instruments But you won't see that being taught in today's schools and universities concerning the topic of physics. But again, most of what they've done is analyze everything via mathematics. Mathematics is outside of the mind. In my case, I thought of it first and then started turning it into equations. So you have an understanding first, followed by equations, which turned out to be the same as the equations used in Einstein's special principle of relativity. But again, because they didn't really backtrack, they didn't see the foundation. So basically the concept of absolute is thrown out the window and everything is perceived as being just relative, even though it's not. And so forth. So again, in the world of physics, they call c the speed of light. In my case, I call c constant motion. And again, the constant motion or constant speed of light is simply an outcome of this constant motion and rotation in axis across the dimension of time. But again, they teach the students as though c is the speed of light, and so when they try to understand these equations, a little bit confusing. This is why a lot of the teaching goes on just using math rather than the proper explanation. You can even look at videos from Yale University concerning relativity, and they can explain seeing someone else's clock ticking slower and that person seeing your clock ticking slower by using a special clock known as a light clock. That's where you have a mirror and a light source, and the light goes up, hits the mirror, and comes back down. And that's one tick of the clock and so forth. But if this clock is moving, you start here, the mirror's over there, so the light goes like this and then back down. So to an external observer, the light has crossed a significant distance, not just up and down. But to this person who's moving with the clock, it's just up and down. Anyways, I won't get into all the details. But the point is, when you get to the point of explaining seeing the other person's clock ticking slower, both ways, concerning mechanical clocks, the teacher, the professor, says he can't quite explain it. But what I've revealed, showing how measurement instruments change, and your clocks are offset, and you use two clocks to measure someone else's single clock, right? You end up perceiving their clock as though it's ticking slower than yours. But even the observer who's at rest will use two clocks to measure one of these clocks and will get the same result. So it makes it seem like everything's relative, even though there's an actual sound foundation, an absolute foundation making these measurements happen. So a lot of things that are revealed here aren't even mentioned or understood in the world of physics because they're thinking externally, not really thinking at all, via the use of mathematics. So there you go. That's my last little clip explaining this constant motion. Again, shooting the next set of videos is probably going to take some time, but anyways, I'll give it a shot. Okay, signing off.